Uh, Thank everyone. I am Samit a second year PhD student at the Department of Astronomy, Astrophysics and Space Engineering, IIT Indore. First of all, thanks the organizer giving me the opportunity to present our work. Today I'll be presenting on the effect of Earth ionosphere on the epoch of reionization observation with the Radio Interferometer. I am working in collaboration with Professor Abhib Datta and Ms. Oisila Mujumdar. So here is a deep overview of what I am going to cover today. So before coming to the focal point of our work, let us try to understand our work. So this is the reason your signal is situated, and here we are sitting here to observe the signal. So there are a lot of intervening medium when the medium have the signal passes through before coming to us. The currently a lot of interferometers working and to try to detect your signal. Observation of the 21 centimeter signal is the promising probe to detect observation from the received 21 signal from CD and UART is the promising probe for the early universe, and the most of the first generation interferometer like Jan meter radio telescope, GMRT, low frequency array, LOFAR, Martinsel wellfield array, MWA have all set the upper limit of the on the power spectrum of the signal and no detection of the H1 signal. The observation of Deciduous 21 signal is challenges due, because of the presence of astrophysical foreground, so which is synchrotron emission, which is 4 to 5 order higher magnitude than the target signal, and the from the extragalactic signal, the Earth ionosphere, radio interference, frequency interference, and thermal noise, and so on. So the highly next generation telescope such as Epoch Reionization Array, HERA, and the square kilometer array SK1 low will be expected to detect the 21 centimeter signal. So to understand each of these effects, we have to develop an end-to-end pipeline to deal with this effect. And today I am talking about the effect of Earth ionosphere with the to deal with the synthetic observation with the help of SK1 low. The ionosphere ionosphere is described as a various proportional effect on the radio wave from the cosmic signal incident on the ionosphere. The interferometer measures the phase difference between the antennas, so it is unable to identify the total amount phase created by the ionosphere. So instead, interferometer measure the difference of the phases caused by the variance of the take. So when the Earth ionosphere causes the phase effect on the extragalactic signal at the less than 1 gigahertz, and these effects are variance that are directional, means they vary across different directions and causing the apparent shift of the position of the sources from their original position, and the apparent source position offset of the cosmic signal of the source is shown in here, and which is depends on the wavelength of the cosmic signal. So here we consider the ionosphere taken as a thin layer, and the SK low will be housed at the MW location. So the ionospheric condition
for the SK low 1 is same as the MWM. And as the SK1 low field of B is lower than the MWA, so the ionospheric phase effect are lesser than the MWA. So to keep ionospheric error in mind, we have developed an end-to-end pipeline. So the idea is to first generate the true sky and add the corruption and see how much accuracy needed to detect the signal. So our this is how the simplistic schematic of our end-to-end pipeline looks like. Our sky model consists of the signal model and the foreground model. The signal model generated from the 21 centimeters first, and we use the realistic point source as a foreground model. So we have taken telescope configuration having the 2 kilometer baseline around the center station, and we have run our simulation on the Oscar. To incorporate the ionospheric error, we have generated the Ionosphere sky model, which is basically the Kumar visibility, and we subtract the model visibility from the Kumar to produce the residual visibility, and the model visibility is the free from any error. So we use this parameter set for the current realization done for SK1 low, and the field of B is 4 degree and observation time is the 4 1, and the telescope configuration is shown in the right panel. So using the signal model generated from 21 centimeter first and the foreground, which is the DNTS graph, and combine as input, and we have taken and the telescope configuration. When you run the simulation, what you are getting is shown in here, and as we seen is the foreground point source is dominant is here. So next, what we've done, we have done the quantifying image plane performance using the residual RMS data. So first of all, first we generate first we calculate the RMS noise from the residual data in the data image, and what you see here, sorry, the 0.005% of the ionospheric error is the tolerance for the source position offset for RMS below the signal level, and if above beyond this percentage error, the signal is not detectable, and the signal level is shown in here, is observed by the interferometer. And next, what you've done, determine the spherical done the power spectrum estimation in the delay domain formalism, and the visibility is the correlation of the electric field between the two antennas, and the inverse Fourier transform of the visibility gives us the delay domain. So we have done the spherical average power spectrum from that from the delay visibility, and is shown in the equation shown in here, and we have done the spherical average after binning. Spherical binning, we can we get the spherical average power spectrum, and if the signal power it is not decided that the for foreground avoidance or removal or any other method is used to detect the 21 centimeter signal power. So we have used all the K mode available from this. So then the same study have done the Mujumd et al, and he saw that the power spectrum estimation tolerance level for antenna based gain error is 0.01%, and the position error is 0.1%, and the assumption is that the smooth foreground is confined in the horizontal area of the K in K space at the smallest K per parallel level, as the chromaticity of the instrument in instrument result that the mode mixing where the power transform forward from the angular scale to the frequency scale at the increasing the k perpendicular scale. So as you know, the point source resided in the k perpendicular scale in the largest k largest k perpendicular scale. So as we higher up the corruptions, we see the we cannot detect the signal because the foreground leakage to the UR windows as the increasing the k perpendicular scale. Next, what we done is spherical average power spectrum. So first we add the corruption and varying this error and see what the effect on the 21 centimeter signal extraction. So the red color is shown in here is the signal power and the 0.005% of the ionospheric error is this shown in the orange color, and 0.05 ionospheric error is below this signal level. So we can detect the signal, and above this percentage error the residual foreground started contaminate toward your window, so we cannot detect the signal. So to summarize, we develop an end-to-end pipeline for synthetic observation, and in the current scenario, the calibration and position error and the ionospheric error we have incorporated, and we mainly focus on the CD and EO signs. So we have generated the Earth atmosphere. We have simulate to comprehend and quantify the effect of Earth atmosphere, and we show that the power spectrum analysis the tolerance level up to 0.005% of the ionospheric error. And I already mentioned that I have used point source as a foreground model. So we have to incorporate the diffuse emission of our pipeline and see how the performance goes on, and see what are the tolerance level. And the skill missing are the primary wave connection and the thermal wave. So the bottom line is to combining these effects gives us the precision radio observation for the next generation telescope like SK1. Thank you.
So thank you, Samit. So we can have a few questions.
So your TEC is it's direction dependent, or it's a constant screen across the sky?
See, it depends on time.
Depends on time, but what about directions?
I not consider that. Actually,
Okay.
it is decreasing with the increasing the iron at the depth. It means when signal passing and
No. So the other way to ask the question is, will it introduce a direction dependent gain in the visibilities, or it can be mimicked by an instrumental gain also?
what is that?
See, the gain errors also comes from the instrument, right? So this 0.005%, can it be also equivalent to an instrumental gain error, or
Basically, the angular displacement from
can it be equivalent to an instrumental gain error, or it is just?
Yeah, but I mean, currently I think he's taking just a single ionospheric phase across the entire
just a
field of
single.
view. Yeah, so that is basically antenna dependent
Fine,
error.
fine.
Yeah, but slowly as these things are validated, slowly you can put patches here.
The other comment was that this you have done for point sources, right? So for which the visibilities are very well known, kind of constrained to very high accuracy. When you try to do it for the diffuse foreground, subtracting the visibilities, the model visibility is much difficult because you really don't have a very good signal to noise estimate of the diffuse foreground as accurate as point sources. So there one try to subtract at the power spectrum level, but that also fails sometimes.
So let's thank the speaker